For the function f of x equals to x times e to the negative x, find all horizontal asymptotes, find critical numbers, find the interval where f is increasing, find the relative extrema, and then sketch the graph. Let's try this problem. First, find all horizontal asymptotes. Asymptotes are found by computing the limit of the function as x goes to positive infinity and also x goes to negative infinity. You have to find these two limits, and if any of them gives you a finite value, if it converges to some finite value, then y equals to that number will give you the horizontal asymptote. So here we have x over e to the x, because negative powers are 1 over. Negative powers mean reciprocal. And we learned earlier that exponential functions increase faster than any other polynomial. So this will just become 0, which means y equal to 0 is a horizontal asymptote. Okay, let's try the same thing here. Limit, well, this time it's a little different. This is negative infinity. If you try to plug in negative infinity here, this time you see that negative of negative is positive, so you have e to the infinity power. So what is that? E is like 2.7. So if you put a large number here, this is going to increase to infinity. That will be huge, right? So this is a very, very large number. Infinity is also a very, very large number. And you multiply them, what do you get? You also get a very, very large number, but there's a minus sign. So this limit would be negative infinity. And therefore, what we end up with is, here's y equal to 0, but there's no finite number here, so we don't get any horizontal asymptote in this second one. So the answer would be just y equal to 0. The answer would be y equal to 0. Find all critical numbers. Now, when you find critical numbers, you should be aware of domain, because if you get a number that makes f prime equal to 0, but somehow it's not in the domain of the function, then that's excluded from being a critical number. Now, thankfully, in our case, there's no limitation to plugging in anything into x, nor e to the negative x. So the domain of this is all reals. Exponential functions are defined in all reals. Polynomials are defined in all reals, and therefore this function is defined for all reals. Now, critical numbers are points where f prime does not exist, or where f prime is equal to 0. Hence, we will differentiate this. And it's a product of two functions, so you must use the product rule. I mean, there's another way to approach this, which is to write e to the negative x as 1 over e to the x, so it becomes x over e to the x. In that case, you can make this as a quotient, so you can use the quotient rule after doing this transformation. But quotient rule is so complicated that it's much worse than the product rule, that you don't want to use it. So let's stick to the product rule. X prime is 1. Now this one requires a chain rule because negative x is nested inside the e to the x function, right? So using the chain rule, we differentiate the outside function. E to the x is e to the x, so the outside function doesn't change, but then this inside function must be brought outside in order to be differentiated, and therefore this will be 1 e to the negative x and plus x times e to the negative x times negative 1. Now, notice that they both have e to the negative x as a common factor. So let's simplify this by making it as e to the negative x times 1 minus x. Okay. Now this function is always defined because exponential functions are defined for all reals. 1 minus x is a polynomial. So there is no case where f prime is undefined. Therefore, critical numbers will be numbers where this derivative is equal to 0. So that means either e to the negative x equal to 0 or 1 minus x equals to 0. But exponential functions are always positive. It's never 0. So this cannot happen. This first one cannot happen. And this one would be true if x equal to 1, right? So that's the only critical number. Now once you have the critical number, then what you need to do is you want to put that on the number line, and that number divides the entire number line into two intervals, right? And to figure out where f prime is increasing or decreasing, and to figure out where the function has a relative extrema, you need to figure out the sign of f prime. It's all determined by figuring out where f prime is positive or negative. So that's why I put the 1, which is a place where f prime is 0. And you just need to pick a sample point before 1. I like 0, so I'm going to pick 0. And then I like 10 because 10 is a big number and it's easy to compute. So these are the critical numbers, the sample points these are the sample point I pick in these intervals. And then let's plug it into f prime. Oh, I need to know the f prime. F prime was e to the negative x 1 minus x, so f prime of x equals e to the negative x 1 minus x. Let's try to plug these numbers. So f prime of 0 would be e to the 0th power 1 minus 0, which is anything to the 0th power is 1 times 1, which is 1. And I'm not really worried about the value. I just need to know if it's positive or negative, and I see it's positive, okay? Then f prime of 10 would be e to the negative 10 times 1 minus 10, which is negative 9 e to the negative 10. And e to the negative 10, exponential functions are always positive. So you have a negative number times positive number, so that's negative. So over here it's negative. What does that mean for the function? It means that the function will be increasing before 1 and decreasing after 1. Okay? And therefore, we see that at 1 we have a relative maximum. And if you plug in f of 1, if you plug in 1 into f, you get 1 times e to the negative 1, which is 1 over e, because e to the negative 1 means 1 over e. So from these two, I see that the function will have a relative maximum at 1 comma 1 over e. And the function will be increasing from negative infinity to 1, right? This domain, the interval left of 1 will be starting from negative infinity and ends at 1. So the answer for this would be negative infinity until 1. Okay, we can gather all the information that we have so far to draw the graph. So let's think about what the graph would look like. We know that it should be increasing and then decreasing, right? Okay, so let's sketch the graph. First thing to remember is we found the horizontal asymptote to be 0, so I know that the function will be getting closer and closer to this dotted line. Another thing, although we didn't use it to answer anything so far, but we do know that as the function goes to the left, it goes down to negative infinity. In addition, we also know that if you plug in 0, you get 0. Okay, so f of 0 is 0 times e to the negative 0, which is a 0. So it has to pass through this point. We also know that at 1, it has this maximum 1 over e, and then it goes down afterwards. Okay. All right. It increases before 1, it goes down, it decreases after 1. So I need something to increase passing through these points, and I also know that it has to go down to negative infinity as you go left. So it must be this, and then as you go right, it should get closer and closer to the x-axis, so the graph should be like that. Okay. Now later on, when you learn curve sketching, you will also figure out the specific point, which is called the inflection point. That's where the way that the graph is curved changes. It's curved. The graph is curved like this, but then it's curved differently at this inflection point. So you'll have a better picture of this graph later on.